Okay. Hi, everyone. My name is Zining. Today, I'm going to present JetUnit, rendering diverse force feedback in virtual reality using water jets. This work was done in collaboration with Jiasheng Li, Ze Yuyan, Dr. Jun Nishida, and my advisor, Dr. Huaishu Peng from the University of Maryland. A single task can involve distinct force feedback. For example, getting an injection. First, you feel gentle, brief touches as the nurse checks you in. And then, during the injection, there is a very intense and sustained sensation. So, here's the question. Can current haptic technology recreate this wide range of force feedback in VR? Well, researchers have explored various methods to deliver force feedback, but most focus on a very specific point in the force spectrum. For instance, Hadro Ring designed a fluid system to deliver gentle tactile feedback on fingertips. Impact Vest can create strong impacts on torso to simulate sensation like a fire blast. Force Jacket used a pneumatic system to deliver various types of force feedback across a large area of the body. But it is still challenging to render the injection scenario, where it requires a wide range of force intensities and frequencies concentrated on a small localized area. So, we propose JetUnit, a water-based VR haptic system that uses water jets to produce diverse types of force feedback. By manipulating the intensity and frequency of the water jets, we can create a variety of haptic patterns, including light touches, strong pokes, wave-like sensations, and different pathing theorems. You may wonder, why water? We chose water as the medium because it is incompressible. Any applied force can be transferred almost entirely to the target. And this efficient energy transfer makes water ideal for delivering high force and precise sensation feedback. Well, emitting water jets is very simple. You just need a water tank, a pump, a valve, and a nozzle. To adjust the intensity, we can control the power of the pump. And to change the intensity, we can adjust the duration of the valves on and off cycles. However, applying water jets to the user is very challenging because we need to keep them dry. So we introduce a compact and self-contained chamber into the system. And this chamber is designed to contain the water while remaining the force. And this brings us to one of the major contributions of this project, the design of the chamber. The design process unfolds as follows. First, we select the material of the membrane to best maintain the force intensities while ensuring the user remains dry. Next, given that the water is confined in a very small chamber, water accumulation becomes inevitable, and this can diminish the force output. To address this, we need to upgrade the structure of the chamber design. And finally, we tune the nozzle diameter to optimize the intensity of the water jet force. Let's dive into the details, starting with the membrane selection. We tested 3 materials, each varying in thickness and elasticity. Material 1 is an ultra-thin, non-elastic polyethylene. Material number 2 is a thicker, non-elastic polyethylene. Material number 3 is a thin, elastic nitrile rubber. And these are commonly used materials for food preservations and glove manufacturing. And based on the overall performance, material number 3 stands out for having the highest force transfer efficiency. However, even with the material number 3 as the membrane, the force is still significantly reduced compared with the bare water jet, which has no membrane. And this is because water bouncing off the membrane leads to the accumulation and turbulence, which block the subsequent water stream from reaching the membrane. To address this issue, we updated the chamber structure design. First, we added a protective sleeve between the nozzle and the membrane to isolate the water jets from any accumulated water. And next, we integrated a ring channel. This channel is connected to a conduit leading to the chamber outlet. And these two features allow water to escape the chamber efficiently. Lastly, we introduced a recycling pump to quickly vacuum the water from the chamber outlets. And following the integration of this upgrade, the force measure on the membrane greatly increased. Now, it is almost identical to the bare water jets with no membrane. As we know from the fluid dynamics, when the mass flow rate remains constant, reducing the nozzle size will increase the water pressure and velocity. But if the nozzle diameter is too small, it can overload the pump, ultimately reducing the performance of the system. So we need to find the nozzle diameter to achieve the optimal force intensity that the system can produce. In order to do so, we tested 4 nozzle diameters: 0.8, 1.2, 1.6, and 2.0 millimeter. And since the affected area on the skin is very small, it makes more sense to consider force in terms of the pressure. And we estimate the pressure using the formula pressure equals to force divided by the actual contact area. And the result on the right demonstrates that when reducing the nozzle diameter from 2.0 to 1.2 millimeter, the average water jet force increased, aligning with the fluid dynamic principles. However, when the diameter further reduced to 0.8 millimeter, the force decreased, indicating that an overload on the pump system. So we figure out that when the nozzle diameter is 1.2 millimeter, the system performs optimally, with a maximum pressure of approximately at 450 kilopascal. And this pressure is close to, but below, the pin pressure threshold, indicating that our chamber can produce a very strong feedback without causing any discomfort to the user. We also conducted a perception study with 7 participants, and the result showed that water jets from 1.2 millimeter nozzle were the most intense without causing any pain. In the end, we picked 1.2 millimeter nozzle for our chamber design. In summary, our chamber design features a nitro rubber membrane, upgraded chamber structures, and a 1.2 millimeter nozzle. These enable us to deliver force feedback comparable to the bare water jet without user getting wet. And when we integrate our finalized chamber into the system, alongside a water tank, water pumps, valves, and control circuit, this system, we can achieve a broad range of force intensities and frequencies. This further enables JetUnit to generate more complex force patterns, including waveforms like sawtooth, sine, square, and triangle waves. We conducted a user study with 11 participants to evaluate JetUnit's ability to render various haptic patterns in VR. In the study, participants need to complete a mission where they act as a chosen warrior. First, they receive a touch-based VIN check. And then they got an injection to implant a magical chip into their body. Later, they could activate the chip to power up their shields, and the powering up process triggered different waveform signals. And finally, they were sent to a battlefield where they defend themselves with the shield against the shot fired by the flower monster. And the result from the user study confirmed that participants can accurately perceive different types of force feedback produced by the JetUnit. And they agreed on JetUnit can enhance their enjoyment and realism across various interaction scenarios. Overall, JetUnit has proven effective in delivering diverse haptic patterns with a wide spectrum of force intensities and frequencies. For future work, several questions raised during the demo day align with our planned next steps. First question, can the device be applied to a larger area of the body? Well, currently we're using a single unit system as a proof of concept. But in the future, we plan to integrate multiple units, which enable us to cover larger areas of the body and also work towards a full body haptic system. Can the water jets be smaller to match the size of the needle? We are exploring the use of adjustable nozzle to control the size of the water jets. And this would allow for a more precise and realistic sensation that better match with the visuals. And the last very common question is, can you change the temperature? Yes, we are considering the integration of the thermal feedback by allowing water temperature adjustments. And as highlighted in today's hot interfaces sessions, thermal feedback is a valuable feature. We would love to use water for delivering temperature sensations and enhancing the overall user experience. This is the end of my presentation. Thank you for listening. I'm happy to take any questions.
All right, thank you for the interesting talk. If you have any questions, please come up and ask questions.
Hi, this is Yu from Zara University. This might be a silly question, but can you explain a little bit how is it different from just driving a needle with a linear motor?
With a linear motor, can you achieve a very intense force feedback? Actually, we tested with that. One of the drawback for servo motor is that because we're also targeting to have a wide spectrum of the force frequency as well, and the servo motor cannot reach as high as the frequency that our system can produce. So that's one of the reasons we, in the end, choose the water that could achieve for wider range of capability that system can produce.
Okay. But I guess if you consider the portability of the entire device, you have the water pumps and the water tank, whereas I think maybe a motor-driven system might be more portable. What do you think about that trade-off between?
So I think your question is it kind of matches with one of the limitations that we currently have is the portability and the weight of the whole system. It's true that the pump and all the tank that I I used in the prototype right now is relatively large, but compare it with the air compressor is already quite compact. And if we are targeting to make a future product that can be more smaller and portable, that can be wearable on the body, we need to search for the the specific product off the shelf that we can use. But I don't think that will be an issue, depending on the requirement or request from the product.
I have a quick question, very interesting talk. How you mentioned about the temperature feedback for the future work. How would you, have you thought about providing different levels of temperatures, like hot and cold?
Oh, yeah. Actually, this is my next project that I'm targeting to do. So with using the water, I think currently water we are using either Peltier to heat up or cooling down the water. I think that would be a very interesting direction that we can integrate that type of thing into our system. And the challenge would be how we can switching the temperature, and that's one direction or one research question waiting to be resolved, and also time delay and duration stuff. But yeah, definitely I think it aligns with my research goal. Yeah.
Right. You have a question? Okay, just a quick.
Hi, Uli from the Max Planck Institute. Just a quick question about the water pressure, I'm seeing that there's a lot of vibration that happens when you're activating the jet, just like looking at the video. And I'm just curious if you found that that might be, affecting how people perceive the feedback, right? Because you're generating the feedback itself, and then you're also getting all the vibration from the water sloshing around inside the tank.
Yeah, that's a great question. So the vibration actually is something that we try to minimize in the whole system, as is produced by the noise of the pump. And you observe that because like the tubing and the whole prototype right now are used the tough material, and they can deliver the vibration like quite efficiently. So we add another layer of foam to try to minimize and avoid the vibration, and try to isolate the participant with that type of like distract vibration that we do not want to conclude in the haptic patterns. But yeah, that's a great question.
All right. Okay. Thank you for the talk.